All right, guys, this is Chapter 15, Part 5, the Solubility-Product Constant. Okay, so with equilibrium, there comes a lot of different Ks, and right now you've been writing them like this, and I want you to realize that that is generic. There are Kas for acids, Kbs for bases, Kcs when we're using concentration, Kps when we're using pressures. There's all sorts of different Ks, and we're just going to learn about one of them. We're going to learn about the solubility product constant, the KSP. And solids are always omitted from the equilibrium expression, but the KSP shows the solubility of an ionic compound, okay? And so when you learned about the solubility rules back in like chapter, I don't remember what it was, but when you learned that alkali metals are always soluble, and hydroxides are only soluble when they're with something, and sulfates are only soluble with these things. There were some things that you denoted as insoluble. Those insoluble substances aren't really insoluble. They're marginally soluble, or soluble sometimes. And the KSP shows how soluble those things are because it's actually in equilibrium with the solution. So if the KSP is big, that means the compound is very soluble. But if the KSP is small, that means the substance is not very soluble at all. So let's look at some of these and see what I'm talking about. So barium sulfate has an okay KSP of 1.07 times 10 to the negative 10th. That's still pretty small. And what that is basically saying, if this is barium sulfate, then it's going to be in equilibrium with the aqueous ions. And since it's somewhat small, it's going to be marginally soluble. There's not going to be very much of each of those in solution compared to this solid. And so that's what a KSP is. It's showing how soluble something is. So here, calcium carbonate is slightly more soluble than barium sulfate. And here, calcium sulfate is way more soluble than barium sulfate because this number is bigger than this number. Because remember, this is how many times we divide by 10. And we're only dividing this 7 by 10 5 times. Whereas in this one, we're dividing 1 by 10 10 times. So this is a bigger number than this top one, which means calcium sulfate must be more soluble than barium sulfate. All right, so we're going to write some KSP expressions, and you're going to have to know your charges, especially for your main group metals. So if this is our salt, calcium fluoride will break apart into calcium ions with a 2+ charge and 2 fluoride ions, because there's 2 of them for every 1 calcium. And so our KSP expression would look like that. So if we do some more, we have barium sulfate, which I already wrote on the first table. Here is the equation. And so the KSP for that, the expression for the KSP would be barium ions times sulfate ions. And there's only one of each, so they're both raised to the first power. Remember, we do not include those solids. And so manganese 2 hydroxide, that would be our solid, and we would get manganese 2+ plus 2 hydroxides. And I know that this is 2+ because I have 2 hydroxides, and each hydroxide is -1. So all of this would be -2, and so this manganese has to be +2 because it's neutral. All right, so we have the KSP is equal to manganese 2+ times hydroxide squared. And then PbI2, both of these are aqueous. Ions are always aqueous in solution. So we have KSP is equal to iodide squared times lead-2. And it doesn't matter what order you write those in, as long as they have the right exponents. All right, using KSP to calculate the molar solubility. The molar solubility is the solubility of the substance in moles per liter, so in molarity. If you have AgCl, 1 mole of AgCl dissolves and makes 1 mole of each, the silver ions and the chloride ions. Therefore, the concentration of each ion will represent the molar solubility of the original solution. So to find the molar solubility of barium sulfate, you would first define the molar solubility. We're going to define it as S, as the barium concentration and the sulfate concentration. So we're saying, okay, S is going to be equal to barium ions and sulfate ions. So I'm going to go ahead and write my equation down again. And I know that my KSP will be equal to barium times the sulfate. And then I'm going to plug in my KSP. And I'm going to say, okay, S will be equal to both of these. They have to be equal. They have to be equal because if one of these is made, one of these has to be made because they were together once. So I'm going to say 1.7 times 10 to the negative 10 is equal to S for barium times S for sulfate. So now I have 1.7 times 10 to the negative 10 is equal to S squared. And so if I take the square root of both sides, that would give me S. And so that's 1.3 times 10 to the negative fifth. And that would be the molar solubility of barium sulfate. These calculations can get kind of complicated. This is as hard as I will make it. And I'm not even going to try to include very many of these. You might see one of them on your test, but mostly you'll be writing equilibrium expressions for KSPs. And you will also have to write the reactions for the KSP, so the equilibrium reactions. All right, so everyday chemistry, hard water. Many areas of the United States obtain their water from lakes or reservoirs that have a significant concentration of calcium carbonate and magnesium carbonate. And those salts dissolve into rainwater. Water containing these salts is known as hard water. And so hard water is not a health hazard because we need calcium and magnesium in our diets, but the presence in water can be annoying. And so if you look at this faucet here, you can see the hard water buildup on the faucet, and it's because they have low solubility constants. And so water can easily get saturated with too much of this stuff. And then a drop of water, when the water evaporates, we have a lot of this buildup left behind. And so if you see that, if you know chemistry, you can get rid of it pretty easily, but it can also then, the substances used to remove that stuff can also damage certain fixtures in your bathroom. So it adds to all sorts of things. So that's real world solubility product stuff.